Hi, Year 9. Let's go ahead and take a look at gradient and how that relates to a direct proportion. So a direct proportion is just a certain type of linear equation. We've been practicing with lines that usually have a y-intercept and a gradient, and we're going to look at a special kind of line. So it's a linear relationship that looks like a diagonal line. However, it specifically always goes through 0, or where the origin is. So let's take a look at why we might need to know what a linear relationship that's a direct proportion actually is. But remember, it must go through 0. The line must pass through 0. Otherwise, it's not a direct proportion. So looking at our first example, let's go ahead, and if this were my paper, I would go ahead and set it up so that we're walking through this together. It says to write a simplified rate of 80 meters per 10 seconds. So if I have 80 meters per 10 seconds, and I wanted to simplify that, remember we're just going to reduce, so 80 and 10 can both be divided by 10. So therefore, we actually reduce this down to 8 meters per second. So now we have a rate of 8 meters per second. Second step is to write an equation that now relates the amount of meters that were run in a certain amount of seconds. So what we just found, this rate that we found of 8 meters per second, is going to be our gradient, or our slope, that is m. So our gradient is going to be 8, the 8 meters per second. So when we write an equation, we're going to say y equals, and then we're going to use our gradient to multiply by our input of x. So what we're really thinking of is if we let x represent the number of seconds that we're running, so if x is representing the number of seconds, and we multiply that number of seconds by 8, because for every second we run 8 meters, then our output y is going to be how many meters we've run total. So 8 multiplied by however many seconds we run gives us a total number of meters that are actually run. So we're just relating our seconds to our meters with that gradient of 8. So remember, we said that a direct proportion is a line that must pass through 0. So let's go ahead and see what that looks like. So my third step is going to be to graph this. So I'm going to go ahead and set up my x and y axis. Alright, so I moved over here since we have a little more space. And what we're looking at is if my x-axis is representing the number of seconds. So let's say 1 second passes, then 2 second passes, and so on and so forth. And my y-axis represents the number of meters. So since we're saying that for every second we run 8 meters, so that means our first point wouldn't be until 1, 2, 3, 4, 5, 6, 7, 8. So my first point that I'm going to graph is if I run for 1 second, that means I have run 8 meters. So I have a point right here. If I don't run at all, though, then I've run 0 meters. So here's my point on the origin. And what winds up happening is I have a straight line between 0, 0 and 1, 8. So I cross through the origin, and this makes a direct proportion. Alright, so let's try the same idea with this example from your textbook. Water is poured into an empty tank, and it takes 3 hours to fill the tank with 6,000 liters. So the very first thing that I want to do is simplify this ratio. So if I am pouring, it's 6,000 liters for 3 hours, then what this reduces down to is 2,000 liters per hour. Okay, so 2,000 liters per hour. Now, like to look at part B where it says draw a graph of volume of liters versus the time in hours. So if I'm looking at my volume as opposed to time, we'll go ahead and make volume our y-axis, and time is always our x-axis, right? Because that's our independent variable. So let's go ahead and graph that as our x-axis. So our volume is going to be the y-axis, and our time is going to be the x-axis. And what it's saying is draw a graph of the volume versus the time. So in other words, if 1 hour passes, we're going to wind up filling up 2,000. So let's do a little skipping here. If we let our each of our values here on the y-axis represent 1,000, let's put 2,000 right here. So after 1 hour passing, we have now filled 2,000 liters. So we have 1 point right here on our graph. And if this continued, at 2 hours, I would have filled 4,000 liters. And after 3 hours, it would have been 6,000 liters. So I start to get this line. And remember, if I didn't have any hours pass, I would have no liters. So I'd have a point at 0, 0. So if we connect those dots, we'll get a direct proportion that goes through the origin, and it connects our dots like that, our points like that. So that's representing our relationship of liters per hour. Then it says, what's the gradient of your graph? Well, my gradient is my rise over my run. So if I think about starting at the origin and how much I have to rise and then run in order to get to that first point, I'm rising 2,000 and running 1. So my gradient for CI winds up being 2,000 liters. And my rule winds up being volume is equal to 2,000 multiplied by every hour of time. So I could also look at that as y equals 2,000x. And last but not least, why do we even make these rules? So what can they help us do? And part D is going to ask you to find the volume after 1.5 hours. So if 1.5 is our time, or our x value in this problem, we can substitute it in. So in order to find our volume, we can say that I have 2,000 liters for every for every 1 hour. So if I have 1.5, I'm substituting that in to my time. So 2,000 multiplied by 1.5 would wind up giving us the amount of volume that I actually have in this tank, which is 3,000 liters. And then the same goes for the second one. It says, what's the time to fill 5,000 liters? All right, so this one's a reverse. If it takes, if we want to figure out what the time is, then I will not know what my x is, but I do know that my volume is 5,000, and that equals 2,000 multiplied by whatever time it takes. So the reason why we are going through this is you're thinking back through how you solve equations. So in order for me to get the t by itself, I need to divide by 2,000, and then I can figure out how long it's taking me to fill this tank, which is about 2.5 hours. So just thinking back through, we really are just setting up a linear equation. So y is equal to a gradient times x, your input, and we're just relating it to whatever the situation is that's given to us. I'll see you guys next time.